Welcome over to the Yaka Digital Network. If a single light bulb burns out in your living room, why doesn't it shut down the TV or the fridge in the rest of the house? The answer comes down to exactly how the electrical components are wired together and the specific paths the current is forced to travel from the main supply. Getting a grip on these pathways, specifically the rules of series and parallel arrangements, gives you the tools to analyze both basic electronic gadgets and the safety of your own domestic wiring. Let's start with a series circuit. Looking at this split screen, a series arrangement is like a single water pipe with multiple narrow pinch points. Because there are no branches, the flow has no choice but to squeeze through each obstacle one by one. Because the current must pass through every single resistor, the resistance simply stacks up. Mathematically, you just add them together. Three 6-ohm resistors in series give you a total resistance of 18 ohms. Notice that the amount of current entering the circuit is exactly the amount leaving. The current remains constant through every component. It just encounters more total resistance along the way. But relying on a single path creates a physical vulnerability. Because the voltage is shared across the components, if one fails, the line is broken and the current stops entirely. You can see this limitation on older holiday decorations. One burned-out bulb means the whole tree goes dark. To avoid that total blackout scenario, standard domestic wiring uses parallel circuits. When you look at how homes are connected to a power grid, the wiring provides independent paths so that each appliance receives the full mains voltage. Think of a parallel circuit like a busy transport hub. Even if each individual lane is congested, opening up multiple separate branches gives the traffic more options. In electricity, adding more branches in parallel actually decreases the overall resistance. Here is a diagram showing a parallel circuit with 3 distinct branches. The voltage across each resistor is identical, but the total current splits, sending a fraction of the flow down each path based on its resistance. Calculating the total resistance requires reciprocal math. We add 1/6 plus 1/6 plus 1/6. That gives us 3/6, which simplifies to 1/2. Many students make an error here by stopping at 1/2. That fraction is 1 over the total resistance. You must flip the fraction upside down to get 2/1, giving a final answer of 2 ohms. Connecting 3 6-ohm resistors in parallel drops the total resistance to just 2 ohms. In any parallel circuit, the total resistance is mathematically guaranteed to be lower than the smallest individual resistor on the board. In exams, you are rarely handed a pure series or pure parallel circuit. You are tested on combination circuits. The strategy for solving these is strict. Always start by isolating the parallel sections first to calculate their equivalent resistance. By applying our reciprocal formula to these 2 parallel 6-ohm resistors, we calculate an equivalent resistance of 3 ohms. We can now treat that entire highlighted block as a single 3-ohm resistor. What remains is a straightforward series circuit. You simply add the original 6-ohm series resistor to our new 3-ohm equivalent block, giving you a total circuit resistance of 9 ohms. Any complex circuit is just a set of simple circuits layered together. By patiently chunking it into smaller parallel and series rules, you can map out the entire system. Let's apply this mathematical reality to a practical safety hazard. If you plug a heavy-duty heater, a fridge, and an iron into a single multi-plug extension cable, those sockets are wired in parallel. This graph illustrates Ohm's law in action. As you add more appliances in parallel, the total resistance of the circuit drops. Because current equals voltage divided by resistance, forcing that resistance down causes the current drawn to spike massively. This excessive flow of electrons generates intense heat along the wiring. This is how overloaded extension cables melt their insulation and trigger electrical fires. To review, series circuits maintain constant current, share voltage, and their resistance adds up directly. Parallel circuits maintain constant voltage, split the current, and require reciprocal math to find a total resistance that is always lower than the individual branches. For more step-by-step problem-solving guides across all your subjects, head over to the Yaka Digital Network at yaka.cc.